In this video segment, we're going to talk about simple and compound interest, which is actually a fantastic application of exponential functions and very realistic. It's something that everybody should know at least a little bit about. We'll introduce at some point a new concept about logarithms, which will help us do a variety of things. We'll come back to that. So let's start off with an example. Suppose that you give a friend a loan, or your friend gives you a loan of $100, which we're going to call the principal or present value. He doesn't mind when you pay him back, but asks that you pay him 10% of the original borrowed amount every year that you keep it. Does this scenario, where the amount you owe as a function of years that have passed since you borrowed the money, represent linear or exponential growth? Well, let's plot those two variables. So we're going to have the amount owed as a function of the years that have passed. So I am going to call this years t, and I'm going to call the amount owed, I'm going to call it F for now, and that's, or F, yeah, I'm going to call it F for now, and that's going to stand for future value. So what I owe him in the future. We'll talk more about that later. So I know that initially, if I kept the loan for 0 years, I would basically owe him exactly what he borrowed me. If I waited 1 year, I'd have to pay him back the $100, plus I would have to pay him 10% of the $100. So I'd have to pay him 0.10 of 100. Now you're probably saying, Milos, you've convinced us to multiply 100 by 1.10 instead of adding the original back to it. But let's see what ends up happening. So 10% of 100 is 10, and that comes out to $110. After 2 years, we're taking the original amount, 100, and to that we're adding 10% of 100. But wait a minute, that would give me exactly 110. I am now basically adding this $10 fee on 2 times, because I've already I pay it once for 1 year and then once for another year. So in that case, I would pay $120. For the third year, it would be 100 plus 10% of 100 times 3 years. And notice again that this is based on the 10% of the original amount borrowed. So of 10% of the original $100. Okay, so it looks like we have a linear pattern. That is, the growth amount is $10 every year, regardless of what is already owed. If we want to write a function that outputs the amount you owe him as a function of years that have passed since you borrowed the money, well, we call that the future value. This is the amount owed. So the amount owed is determined by the principal, which is $100, plus the rate at which you're paying interest, times the base amount, the principal, multiplied by the number of years that have passed by. So in other words, this would just simply reduce down to 100 plus $10 times the number of years. Okay, so now another question we might want to ask is, how much will you owe him if you pay him back in 3.5 years? Okay, well, we can probably figure that out. For some people would basically be able to say, well, you're going to pay him $35 because you're going for 3 full years. 3 full years at $10 a year would be $30, but then you're also going for another half year, which half of 10 would be 5. But this formula would output 135. So we would pay him for the partial year as well, not just for the full years that we use. Okay, well, what's a more general, what we've dealt with here is called simple interest. Simple interest is interest, and of course we understand interest as basically paying money on top of anything that you already owe, or somebody paying you money for money that you loan them. So this is interest paid is only based on the principal. Remember, this is what we were calling the present value. I'll just denote that PV. And the way we calculate it is the future value, so the amount owed, would be the principal, which I'm gonna label that. I'm gonna label it with a P, which stands for principal or present value, plus the base amount, which is P, times the rate, which I'll just call R, so R would in this case be 0.10, and then we of course multiplied all of that by the number of years. So simplifying this, if I were to factor something out, I could actually factor out a P from both terms. Well, what happens if I divide out a P from P? We know that P divided by P would give me 1, and I know that P times R times T divided by P would give me 1 times R times T. So if you use the distributive property, P times 1 is P, P times RT is PRT. So if you think about this, this is a linear function. Now this works just fine as well. We just wrote it another way that you might see it appear in other books. So this is the simple interest formula. This allows us to predict how much you owe based on the principal amount, the rate at which you borrow, and the time in years. For the most part, simple interest is not something that's very commonly used anymore. Oftentimes we use what's called compound interest. And compound interest is basically, I think a lot of people think about it this way. It's interest paid on principal and any interest already paid. So the beauty of this, well, if you're the person giving the bank your money, so excuse me, that was paid. The beauty of this is if you're giving the bank your money, like in a checking or savings account, they're paying you interest not only on top of what you originally put in, but on top of any interest that you've already earned from them. So that's why we call it compound. It's a compound process where it's basically one interest on top of another interest on top of another interest. Interestingly enough, we've already seen this. We've already seen this with population growth, because we're saying that population is going to grow on top of any population that's already there. So if your population starts at 100 and it grows by 7%, let's say, then next year it's going to be 107. If that 7% growth continues, we know that 107 will be the next thing that gets grown by 7%. So the amount will be slightly bigger than 7 people. So I don't know what this is right off the top of my head, but point being, we've already done compound interest. And compound interest itself is an exponential process. So let's take a look at an example. The bank works in a couple of ways. First of all, every bank offers, so when I'm saying offers, let's say you're putting money into a bank. Now it really doesn't matter whether you're borrowing or you're giving the bank your money, other than the fact that the bank wants more interest from you for borrowing their money than they're willing to give you to borrow yours. So it really doesn't matter whether I say offers or requires that you pay. It's the same idea. They offer an annual percentage rate whenever you go and decide to put your money in with that bank. Now that's often referred to as the APR. Okay, so let's say a bank offers 12% APR compounded monthly. Compounded monthly. So what does this mean? This means that they will pay you 12% annually, but will give it to you in monthly chunks. So here's what they do. So they tell us they're going to pay us 12% annually, and they're going to pay us interest on a monthly basis. That's what the word compounded means. They're going to pay interest on a monthly basis. Well, what they're going to do is they're going to say, okay, well, we're going to give you 12%, but we're going to give it to you evenly across the 12 months. Now, normally we don't divide percentages by months to get the monthly rate, but this is how banks do it. They would say, well, 12% over 12 months means we'll pay you 1% per 1 month. And so basically, they'll pay you interest on a monthly basis. So if you put in $100 as your principal or present value, well, next month, your future value would be 100 times the monthly rate of, well, they're going to give you your full 100 back, but they're going to give you 1% more. So remember, there's our 100%. On top of that, they're giving us 1% more. And they're going to do that one time because only 1 month has passed. And after 1 month, we would have $101. Similarly, if we did this for 2 months, we would basically take it to the second power. And I don't know what that comes out to exactly right off the top of my head, but we would basically get 1% every single month. So what this gives us then is we have our present value times 1 plus the, what we usually call the periodic rate. In this case, our periodic rate was, for example, was monthly, raised to the power of the number of periods. So, as an example, say you put in $100 into an account that pays 8% APR, but it's compounded weekly. Okay, well, we assume, for simplicity, 52 weeks in 1 year. Okay, so what's the bank going to pay us? In this case, since they're paying us weekly, what are they going to pay us each week? Well, each week they're going to pay us, they're going to take the 8% and they're going to divide it up into 52 weeks. So remember, to get percent per week, we have to divide by weeks. So this comes out to 8 divided by 52 equals 0.15. Now be careful because this is still percent, but this is percent per week. So yes, absolutely, you're getting less than 1% per week. Okay, well, let's say we want to know the future value in 2 years. Well, we know that our future value is equal to what we start with, or what we deposit, which is 100, times, in this case, well, what is the growth factor? Well, we know the growth rate is, I'm going to write this up here, the growth rate is 0.15%, which is equal to, be careful here, 0.15 divided by 100 is going to be 0.0015. So that means that our growth factor would be 1 plus that, because that's the amount of growth every week. And in this case, well, how many, if this is the weekly rate, then how many weeks am I doing this for? Well, in 2 years, how many weeks are there? Well, there are 52 weeks in 1 year. For 2 years, there would be 104 weeks in 2 years. So that means that this is going to get applied 104 times. Now you might say, hey, that's a lot of interest to be paid, but it's also a very, very small amount of interest to be paid. So now we come over to our calculator, we can figure this out. 100 times 1.0015 raised to the 104 power, and we get about $116.87. So that means we would have that much in the account under this particular account. Now, if you roughly play it out, you notice that 8% a year should come out to roughly about $8 a year. So next year it comes out to a little bit more than $8 because we're putting interest on top of interest. So let's take a look at an example. How much would you need to deposit today in order to have enough to pay cash for a new car after college, which is going to cost $16,995, if interest is paid at a rate of 3.2% APR compounded daily? So we're going to assume 365 days in 1 year. And you plan on purchasing the car in 3 years. So in this case, we have to calculate, because interest is paid daily, what is the daily rate? So we have to calculate the rate based on how often it's paid. Well, in this case, it's a daily rate, and we're taking 3.2%, assuming 365 days, they're going to split it up into 300